The presence of water ice at the Moon's poles was first hypothesized in the 1960s during the early lunar explorations. The Apollo missions, which brought lunar rock samples back to Earth, detected traces of water. However, at the time, these findings were attributed to terrestrial contamination, as it was believed that the Moon was completely dry. The idea of a completely arid Moon dominated the scientific community for decades. A change in perspective came many years later, in 2008, when a study conducted on volcanic glass in lunar rocks once again revealed traces of water. This discovery marked an important step toward revising the idea of a completely dry Moon. It is worth noting that as early as 1978, some Russian scientists, analyzing samples collected by the Soviet Luna 24 mission, had published a paper claiming they found traces of water, but their results were either ignored or minimized. In the years that followed, various attempts were made to detect water on the Moon through remote observations, using instruments aboard spacecraft. However, these missions did not yield satisfactory results. The Cassini spacecraft, during its lunar flyby in 1999, failed to confirm the presence of water. Similarly, the 2005 Deep Impact mission and Japan's Kagaya mission, launched in 2007, were unable to obtain convincing evidence. One of the first concrete clues of the possible presence of water ice came in 1994, thanks to the U.S. Clementine mission. It collected radar data from the Moon's south pole, and some observations seemed to indicate that ice deposits might be present. However, the evidence was not solid enough to draw definitive conclusions. A breakthrough came in 1998 with the Lunar Prospector mission, which detected abundant traces of hydrogen at both lunar poles. The presence of hydrogen suggested that there could be frozen water, but direct evidence was still lacking. At the end of the mission, in 1999, the Lunar Prospector was deliberately crashed into the Shoemaker crater in the hope that the impact would raise debris containing water. Scientists observed the event from Earth, but despite expectations, no significant traces of water were detected in the expelled material. Despite these failures, the idea of water on the Moon was not abandoned. In 2008, India's Chandrayaan-1 spacecraft conducted a similar experiment to that of Lunar Prospector, releasing a projectile that crashed into the Shackleton crater at the lunar south pole. During its descent, before the impact, the spacecraft used its spectroscopic instruments to analyze the soil's chemical composition. The data revealed traces of water and hydroxyl groups, confirming that at least in some lunar regions, water might be present, though mixed with the regolith. In 2009, another impact experiment, conducted with the upper stage of an Atlas V rocket in the Cabeus crater, led to the release of hydroxyl molecules, suggesting that water ice might be mixed with lunar soil. This discovery was further confirmed by observations from the Lunar Reconnaissance Orbiter, whose data showed that the surface of certain craters at the South Pole was particularly reflective. This type of reflectivity is typically associated with the presence of ice and represented one of the most solid pieces of evidence to date of possible water ice deposits on the Moon, mixed with regolith. But how can water reach the Moon? One of the main theories is that it was brought by impacts from comets and asteroids. These celestial bodies have constantly bombarded the Moon over billions of years, depositing small amounts of water on its surface. However, the Moon, lacking in atmosphere and exposed to constant sunlight, is a hostile environment for the preservation of water. If exposed to sunlight, water would quickly be destroyed, as the sun's ultraviolet radiation can break the chemical bonds between hydrogen and oxygen, the two elements that make up water molecules. Nevertheless, water can survive in so-called cold traps. These are perpetually shadowed niches located inside deep craters, where temperatures can drop to hundreds of degrees below zero. Under these conditions, ice could persist for billions of years, shielded from sunlight and the high temperatures that characterize the rest of the lunar surface. Another theory suggests that water might be produced directly on the Moon itself. The lunar surface is constantly bombarded by the solar wind, a stream of charged particles, mainly protons, hydrogen nuclei, that travel from the Sun through space. When these protons impact lunar rocks, rich in oxygen in the form of silicates, they can combine with the oxygen atoms to form hydroxyl groups, O. Another hydrogen atom could then bond with these hydroxyl groups to form water molecules. This process might occur primarily in lunar regions exposed to sunlight, with the water later transported toward the poles and trapped in the cold traps. Indeed, the presence of water or hydroxyl groups has been observed on the sunlit surface of the Moon by several space missions, including Chandrayaan-1 and, more recently, by the airborne SOFIA telescope. These discoveries open new scenarios for the future of lunar exploration, as the presence of water is crucial for supporting potential permanent human bases on the Moon. It would reduce the need to transport water from Earth and allow for the production of oxygen and hydrogen for life support and rocket propulsion. Thanks for watching. Don't forget to like, subscribe to the channel, and activate the notification bell so you won't miss the next videos.